All right, so I'll discuss, I want to follow on with both Bruce and Sergey have just done on a couple of levels. One, I'm going to try and give you, we're going to have a discussion of economic science. Now, I want to make 2 points in the course of this presentation. One is going to be to try and illustrate some, in a more detailed fashion, the character of Vernadsky's concept of the noosphere. And we'll see near the end of this why this will lead to the same conclusion as you had at the end of Professor Poulanet's panel. And then have a discussion in the course of that, though, to take up more of what Bruce took up in his, the discussion, the necessary threat, why it is that environmentalism is the most persistent and the most dangerous threat that exists that faces humanity today. We're going to have a discussion of why it is that ideas, concepts such as zero growth, sustainable development, and green energy are going to have to be thoroughly eliminated in order to ensure humanity's survival. Now, the ironic part of that is that most environmentalists wouldn't actually disagree with that point. They would, in fact, they would explicitly present themselves as an opposition to the development of humanity, everything you would consider to be human progress. Their reasons for doing so might be unclear even to them. Now, in general, there's a couple of levels of the dishonesty here. There is a legitimate dishonesty that you get in the misrepresentation of environmentalist arguments. I think one of the elements of that that's most characteristic is the dishonesty when it comes to their reasoning in they attempting to address certain so-called crises. I think most people in discussions have realized that you occasionally get the argument made that, oh, the reason we're worried about rise in we're worried about global warming because we're worried about a rise in global ocean temperatures, and there'll be tons and tons of presentations and worries about the polar bears, etc. And then as a sort of passing thought to try and sell it to the rest of the population, they'll tell you a story about how there are these small island nations which are threatened by the rise of seawater and they'll be wiped out. So somehow over time their presentation is that they're so concerned that over a long period of time this slowly rising ocean water will wipe out the coastal cities and underdeveloped islands. Now, if they were actually concerned about that, they would help to develop these island nations, and it would help to raise living standards, so the kind of catastrophes we recently saw, for instance, in Haiti, would be impossible. But because their concern is not the actual defense of humanity, that argument's never made, and instead you just have that used as a cover for the attempt to prevent the very types of economic development that would save those areas. The same thing happens, it's explicit when you read their discussions of what they think the crisis in Africa is. I remember just recently I read it was one of these journals which had the cover story was something like Crisis in the Congo. And I was sort of interested because I thought that it would be an article that was dealing with the humanitarian crisis that was taking place, that was some kind of an issue dealing with the human beings in the Congo, but instead it was page after page after page of a discussion of human threats to gorillas in the Congo. And it gives you again an idea of the sort of the skewed priority that you get a skewed priority that you get presented by the environmentalist lobby, but then the fact that when they finally do mention anything that's discussing humans, that's mentioned on some level that they care about the well-being of humans is always a cover. Now that's one level of dishonesty, but what I would like to discuss is a deeper level of dishonesty, which is even beyond. It's clear that underneath the environmentalist ideology at all levels is a kind of vicious anti-human sentiment. But to understand the actual agenda of environmentalism as a policy, you cannot look at the environmentalist. Now, this is going to get to something, what I'd like to do is present sort of the inverse of the discussions of policy that come from the standpoint of reductionism or so-called chaos theory. That is, that you won't find the actual cause of the driving force behind the environmentalist within the environmentalist. To understand the actual driving force behind the environmentalist, you'll have to understand something which Lyndon LaRouche has termed the oligarchical principle. Now, this is the principle which governs the behavior of empires. And we're going to take a closer look at this because we'll see that, again, even in the case of an empire, its behavior does not originate from within the specific individual empire. The behavior of a specific empire originates within something that exists outside of that particular empire in the domain of physical principle. And in this case, the physical principle is this oligarchical principle. And once we understand this oligarchical principle, we'll be able to understand why it is that the British Empire, like all past empires, is so interested in promoting the policies that are now known as environmentalists, but which existed, in fact, much earlier under other guises. Environmentalism is not a new phenomenon. But in order to discuss that, to have a real clear concept of what this oligarchical principle is, we're going to have to develop a clear concept of what the actual principle of human development is. What is the creative principle in human society? Because the oligarchical principle is defined solely in opposition to this. Now, to this discussion of the creative principle in human society, obviously human creativity expresses itself in every domain, every sphere of human activity. This is why the area which is best suited for describing this and discussing this is going to be human economics, because this is the study that subsumes all other areas of human activity. The purpose of viewing it here, and again, the purpose of viewing human creativity in the system of human economics as opposed to in the specifics, is because it allows us to get to something that is actually physically more real than what seem to be the sense-perceptual manifestations of human creativity. And in fact, in the course of this presentation, what I'd like to be able to, the question I would like to be able to ask and answer takes the form of something like, where was human creativity before human individuals first appeared on the planet? Now, if that seems like a funny question, it should. We're going to be able to tackle a very closely related question, which is, but gets to the same point, which is, where was life before living organisms first appeared on the planet? Now, the standard view is that that's not a real question to ask. They say that, well, life did not appear on the planet until a living organism appeared on the planet, and that human cognition did not appear in the universe until human beings appeared on the planet. But in fact, as we're going to see here, as we'll discuss, the question of principle is something that pre-exists the specific physical singular manifestation of it. And we'll see that the strangeness of that latter question, the question of where was life before the appearance of living organisms, its seeming strangeness stems simply from the imprecise definition that we have of life. Again, that's because of the fact that we're familiar in general with living things, but not with life per se. In practice, the concept of life is not a difficult one for us. At least we have what Leibniz referred to as we have a very clear notion of what life is, but not an exact one. What does that mean? That means that you're not often confused when faced with an object about whether that object is or is not alive. People don't often confuse a dog, for example, with a table. Or in the course of looking at a dog or looking at most animals, you can recognize these things are alive, and looking at the table, you recognize that that's non-living. So that seems simple enough. And so when you ask, well, what is life? Most people don't put that much effort into it because it doesn't strike them as necessarily a very difficult question. But what I think most people don't realize is when it comes time to try and actually develop a definition for life, you run into very serious problems. And this is the source of the wasted ream after ream of papers in popular science journals, because what happens is somebody comes up, somebody observes every living thing they can think of, and then based on your observation of all these living things, you develop a very detailed definition of what you think life is. Now, NASA has a definition, which I should have brought, I forget, involves, it's capable of autonomous motion, self-replication. They do an entire list of things, but what ends up happening is no matter what definition you put together in those terms, you will always end up encountering something which, based on that definition, now qualifies as life, even though earlier your instinctive intuition about it would not have qualified it as life. And then as a result, you end up, 3 weeks later having an article in a pop science magazine which declares, we've suddenly realized that X is alive. For instance, recently they realized that proteins left on their own are capable of what seems to be a selective response to stimuli. And so every article that came out of that was, well, proteins are now alive, and there was much crisis about it. Nobody thinks, well, maybe we should change our definition. Maybe our definition was imprecise, and it isn't the case that suddenly now proteins must be included under living processes. Sometimes this is used to push the reductionist agenda. People use this to promote the Oparin myth, which is to say that, well, now that according to this definition of life, so we've established a definition of life that will allow us to distinguish dog from table, but based on my definition, I can include X amino acid, and this will then be used in sort of a sleight of hand way to introduce the concept of abiogenesis, although it's never been observed, and in fact, as we'll discuss here, is principally problematic. The approach I'd like to borrow here in actually investigating life as a principle more directly, again, so that we can answer this question, where was life before living organisms appeared on the planet, is a technique I'd like to take from the scientist Vladimir Ivanovich Vernadsky. Now, this is going to be, being able to take this approach is going to allow us to dismiss a number of frauds that have been promoted by environmentalists about the biosphere and about life, and then perhaps put into the political context of why these frauds were promoted in the first place. And again, I'll take these in various orders, but the first thing I'd like to start here with dismissing is the environmentalist fraud that the biosphere is in some sort of a delicate balance. Now, people have heard this often. This is often touted, and in fact, this is often used to explain why human beings should do nothing. Because the idea is that any change, any action that we might take that would be the slightest tweak in the biosphere would cause an enormous crisis, obviously, because all of these systems in the biosphere are so precariously balanced, one on top of another. But this concept of a delicate balance is not true of the biosphere, and in fact, it has never been true of the biosphere. The biosphere itself has undergone extreme changes that will far surpass anything humanity has yet been able to accomplish. And in fact, extreme changes which, if they have any significance for humanity, it's to tell us that we're sort of behind in the sorts of transformations that we should be able to effect. Now, these changes are an expression of what Vernadsky referred to as biological time. There's two places I'd like to look for this concept of biological time, and though we'll go into one more in depth, which is evolution, I'd like the other one to be on your mind in the course of our investigating it, and the other one is what's called morphogenesis. So just have the mental image in your head of morphogenesis, which is the frankly miraculous process that every living organism undergoes, which allows it to begin with a single cell, a single fertilized cell, and develop itself into a very complex adult organism. Now, this is important. I like to start with that in your mind because in that case, I think it's clear that the process is governed by a single idea. You have the single idea of an adult organism. Now, that it's driven by that concept of having an adult organism, even through all of the crises and torments that the organism faces along its way to becoming an adult organism. Now, these are a lot, and it's really significant to have that in mind because, again, the image I like is even simply human children. Now, if you think about first that you've got if you were to try to describe that organism in mechanical terms, you've got something that's incredibly complex, incredibly detailed. Most pieces of mechanical equipment that are that complex are extremely sensitive to bumps and damages and jolts. People know your laptop doesn't survive, falls off several feet. But now think about a living organism. Not only is this something that's immensely complex, if you think about the circulatory system, think about everything that's included in this. This is something that is being built as it's being that complex. So you can imagine something as complex as infinitely more complex than your laptop, but also growing and developing. And then imagine what it is that your 8-year-old does on a day-to-day basis, flinging itself from various high places, from trees, etc., bumping into things. That 8-year-old is rather resilient, not only resistant to damage, it'll experience damage, break arms, break legs, etc., but still manage to follow that path to adulthood, even with certain kinds of extreme sorts of damage. There's something else being done here which would not work if it were simply if the growth of that organism were simply based on the agreement of all the various parts of that organism. If it were organized the way we think of machinery, where the pieces are put together to interact with one another, there's a concept of a one that's required there to direct it. Now, that concept of a one is one of the great mysteries, probably one of the major mysteries of biological processes in general. If you have that concept in mind, though, for a single organism, it makes it much easier to develop that exact same concept for something like the entire biosphere. And what I'd like to sort of put a lie to is the idea that the evolutionary development of the biosphere is somehow a different process. But the standard argument is that somehow the evolution of the biosphere is explained by all of these separate individual competing interests of the various elements of that biosphere. And in fact, what I'd like to demonstrate here is that that's not the case. Not only is it not the case that all of these elements are not building the biosphere from the bottom up, that there is a concept on the much larger scale on the whole, but that concept on the larger scale extends even beyond the confines of the biosphere itself into interplanetary space and beyond. So look, in order to visualize certain elements of this process, we in the basement team, working with Mr. LaRouche, put together this model that Bruce showed you earlier of biological development. Now, this model is going to apply almost any level you decide to investigate in biological processes. This model will apply. The divisions here are, for clarity's sake, to pick a couple of key slices that will draw out the most important characteristics of what we might be able to term here the ontological character of the physical time of anti-entropy. So what we see here, what's on this chart? On the chart, you've got the division of evolutionary history on the planet into the three major periods known as the Paleozoic, the Mesozoic, and the Cenozoic. Now, the Paleozoic means old animal life. The Mesozoic is the middle animal life, and the Cenozoic is the new or novel animal life. Now, each of these periods here, the Paleozoic, the Mesozoic, and the Cenozoic, is definable as a system. And each of these systems has a governing idea which differs from each of the other systems. Though, in the course of looking at them, we're going to have the opportunity to examine a single thread of development that runs through all of them. Now, the development across these successive systems is marked by catastrophic events, which we refer to as mass extinctions. The first one at the boundary between the Paleozoic and the Mesozoic is what's known as the Permian-Triassic extinction, the PT extinction. At the boundary between the Mesozoic and the Cenozoic is what is known as the KT extinction, or the Cretaceous-Tertiary extinction event. So the question is, well, now, is it possible? It's often argued that, well, from the standpoint of the standard Darwinian model of natural selection evolution, it's said that, well, within each of these systems, it can be explained what animals develop on the basis of natural selection. Now, I won't go in, well, maybe a little bit into some of the, there's a lot of humor that can be taken from seeing people do natural selection explanations of evolution. It's actually sort of it seems like it would be it seems like it would be sort of a fun job because it only involves, you can only do it for so long though, because it simply involves making things up consistently. I apologize because the only example I can think of right now is a little crude, but I remember there is a species of flatworm which, as part of its mating, carries out an act which is known as penis fencing. Now, what this means is that these two, the flatworms are each, every member of the flatworm species is a hermaphrodite, and so they're all capable of becoming impregnated, and they're all capable of impregnating. And for at least one species, what they do is and this I didn't bring photos of, you can look up the photo yourself. But they project two razor-sharp phalluses. Each one has two razor-sharp phalluses, and then they have a battle, one with another. They look sort of like cobras as they face off, and they'll lunge, and whoever gets stabbed anywhere in the body first becomes impregnated, and then, and so presumably you lose. So if you read the descriptions of these, you read the description of why that occurred, explained by people who want to use a natural selection explanation for that, and it at first sounds very plausible, and you can find it even on if you look for the Wikipedia page for the penis fencing, et cetera, this is the official explanation that they have on there, where they go through that, well, obviously, childbearing is such an energy-expensive process that nobody really wants to be the pregnant one. So the creatures battle out to see who's going to become the pregnant one, and then whoever loses becomes pregnant, and then you've lost, and it's a very detailed thing, and it makes lots of sense, and they go through why, over a long period of time, natural selection might have done that, and you're kind of nodding, you think, well, maybe it makes sense. I could see why that would happen. But then if you look a little harder, you'll realize that there's another closely related species of flatworm that, when they engage in their battle, each one is trying as hard as it can to become the pregnant one. So then if you read, there's an entirely other explanation for why this happened. This exact opposite scenario happened. And so, of course, the other argument no longer works, that this is a very expensive process, becoming pregnant, et cetera, et cetera. So anyway, the whole point is that you got this, the question of natural selection explanations is simply a post hoc discussion. You can explain anything you want after the fact. As one of my colleagues, Phil Rubenstein, pointed out, even the expression of the popular expression of Darwin, which is not actually attributable to Darwin, but it holds nonetheless as exemplary, the popular expression survival of the fittest is a tautology in and of itself. What does this mean? You're saying that survival of the fittest means that what is fit survives. And that sounds good, right? You expect that if something's more fit, it should survive. So you say, okay, well, so how do you know that something is fit? Well, it survives. And then you say, well, why did it survive? And so because it was fit. And so you say, okay, well, if I'm really going to slim the thing down, all that statement, survival of the fittest, means is survival of what survives. And that is not a very useful statement for anything. It's a tautology. It's inherently a tautological statement. So first, to dismiss that is considered to be what holds within these cones, doesn't work. But those same people who try to promote the question of natural selection are always at a loss for what happens at the extinction events. Again, most of the top writers in this area, on the area of Darwinian evolution, they say, well, at the extinction events is where it does not hold. At those points, it's just simply chaos. Things are too destructive for any kind of adaptation to occur, so we just can't explain anything. All we can do is explain what happens before or after each of those extinction events. But in the course of our work in the basement, working with Lyndon LaRouche, we found something you would expect to be the case, which is that, in fact, there are some very easily quantifiable characteristics which not only explain the development within any given system, but will explain, in particular, the development across these systems. And that the characteristic, the quantifiable element that would explain the development across these extinction events is, I think perhaps for some in here, not surprising, for others very surprising, best understood from the standpoint of physical economics. And the notion that we'll use here is what the notion that Lyndon LaRouche has developed for economics, known as energy flux density. So let's take a look. Okay, well, I don't have what we'd like to take a look at. I didn't get the image of it, but you can see for each of these. Now, each of these systems here, the Paleozoic, the Mesozoic, the Cenozoic, they're characterized by a very specific collection of fauna, flora and fauna. The ones that I think people are most familiar with is the difference between the Mesozoic system and the Cenozoic system. Now, the difference between the Mesozoic and the Cenozoic system, the Cenozoic post-KT is the system that most of us are familiar with. That is, it's at that point, and only at that point, that mammals become a dominant presence on the planet. It's at that point and after that point that birds become dominant on the planet. It's after that that you get flowers. It's after that that you get grass and grasses. It's after that that you get fruits, fruiting plants, which come from the flowers. It's after that that you get bees, the bees that Professor Poulinet's mentioned in his presentation. All these appeared after the KT event. So you can picture, it's useful to get an image in your head of what the pre-KT world was. This was, mammals, fruits, flowers, these things existed, but they all existed in a very micro form. Mammals were largely rodents, birds were few and far between. The fruiting and flowering plants, these are incredibly tiny, insignificant parts of the system prior to the KT. The dominant elements of the system prior to the KT are in that Mesozoic period, it's probably, at least especially near the later end of it. Well, you could characterize that as being the age of the dinosaurs, but where the dinosaurs are just characteristic of a much larger system. You'd primarily dinosaurs, plants that bore no fruits, no flowers, referred to as what we call the gymnosperms. You had an entire system, no grass, no grasslands, no grazing, et cetera, all the idea of grazing animals, et cetera. This all comes post the KT. So just to give you an idea, there's a whole system there. That KT event is often referred to as the extinction of the dinosaurs. But in fact, what it is the extinction of a system of which the dinosaurs were an exemplary part. Now, the dinosaurs are not insignificant, at least when examining this sort of a system, because they represent the apex predator in this period, the Mesozoic. And in general, the apex predator in the Mesozoic was the dinosaurs, reptiles, and then they bear a very close relationship to one another, even though it's the case that dinosaurs are definitely distinct. But for the purposes of what we'd like to discuss here, their similarity with reptiles is sufficient. So here we go. The apex predators in the Paleozoic, so this is the animal that's on the top of the food chain. In the Paleozoic were amphibians. So if you can sort of imagine for yourself a giant salamander, you'd have an idea of what the most deadly predator was during the Paleozoic. If you can imagine for yourself a giant reptile, you'd have a good idea, a giant lizard, you have a good idea of what the apex predator was during the Mesozoic. And if you can imagine very large, dangerous mammals, which we have plenty of, you can have an idea of what the apex predator was during the Cenozoic. Now, all of this we're discussing prior to human activity. Why is that significant? The apex predator of each of these systems is significant because they represent they're at the top of the food chain. That means that everything that gets consumed within that system is sort of at some point passes through, not every single element, but in principle, everything passes through the apex predator. So you've sort of got two ends of it. You've got your food chain is defined by the top of the food chain, and then where this is the apex predator, and the bottom of your food chain, which is, we'd say, the point where the biosphere interfaces with interplanetary space, and that is with photosynthesis. Now, if you have those two as bookends, you can start to build a flux of material. This flux is something that Vladimir Vernadsky described as the biogenic migration of atoms. Now, for our purposes here, we're going to discuss, probably better put, the biogenic migration of matter energy, which means that if you could instead take, and we've done this exercise, instead of, imagine you could put on your glasses that would allow you to see nothing but carbon. So you're no longer viewing the world as separate organisms, empty space. What you'd see in the course of looking out on any scene of organisms would be complex organizations, structures of carbon. But then as you watch these organisms exhale, you'd see portions of the body actually become gaseous in the form of CO2, carbon dioxide, move into the room. So you'd watch the carbon flow into the organism out. You'd watch plants and you'd watch other plant life absorb that CO2. That would become incorporated into the bodies of the plants. So you'd see this flow becoming plant, flowing into animal, becoming animal, flowing out of animal, becoming plant. You'd see this, it would look to you like this continuous fluid circulating. And that continuous fluid circulating would be caught up in eddies, singular, sort of like whirlpools. And these whirlpools that you would see would be the things that you, under normal circumstances, would call, under normal sense-perceptual circumstances, would call individual animals, individual organisms, etc. But these would only actually be singularities in the bigger system. So now, with that view, you can now start to come up with a measure for each of these animals that determines how quickly does that eddy spin the material that's going through it. How quickly does that whirlpool spin? And the quickness of speed of spin of that one whirlpool, especially if it's a big one, if you've got a big turbine that drives the whole thing, the quickness of the speed of that one turbine, in this case we'll use the apex predator as your description of it, that's going to determine the entire turnover, the entire flow of your entire system. Now again, I'd like to make clear that's the entire system. To give you an idea of what that means, if all animal life were to suddenly vanish from the planet, all human, all animal life were to vanish from the planet immediately, in a matter of days, I think it's a couple of weeks, the entire composition of our atmosphere would change and would collapse to an equilibrium, because the entire composition of our atmosphere is constantly replenished. There's a couple of week turnover rate. So over the period of a couple of weeks, the entire content of our atmosphere is recycled through animal life back up into the atmosphere again. So that should give you an idea of how extensive that flow is that's being stirred up and spun around by these little whirlpools, these little eddies. And that's your biogenic migration of atoms. So the metabolism, the metabolic rate of these apex predators in each of these systems will give you an idea of how rapidly that system is circulating in the Paleozoic, the Mesozoic, and the Cenozoic. So let's take a look. What we're going to look at is the difference here between the amphibians, which are dominant in the Paleozoic, the reptiles, which we'll use as a proxy for what's dominant in the Mesozoic, and mammals, which are dominant in the Cenozoic. So probably the best way to describe the distinction here is, I think everybody here has been trained in some kind of energy conservation. We all get trained. You learn you're supposed to, when you leave a room, you should turn out the lights because you're not using them. You should turn off your heater because you're not using your heater, and this is very smart energy conservation. It's why everybody has to use the silly spiral light bulbs instead of the regular light bulbs, because you're supposed to be, this is obviously supposed to be a very smart, we're becoming more energy efficient. Now, that kind of behavior is exactly what both amphibians and reptiles do. They're cold-blooded. And cold-blooded means that you don't use any energy that you don't have at that moment. As you warm up, you use the energy of being warmed up. As you cool down, you go into a dormant state and you relax. They are perfectly energy efficient. The reptile is the biological equivalent of the dumb spiral light bulb. Now, mammals, on the other hand, are absurdly decadent from that standpoint. Now, think about what it means to be a mammal. A mammal is a warm-blooded creature. Now, what does it mean to be warm-blooded? That means that you've got the audacity to say that you need to be at a certain body temperature all the time. Even when you're asleep, even when you're awake, no matter what you're doing, you're going to maintain a body temperature even when it's cold outside. When it's cold outside, you're going to internally maintain a certain body temperature. That is the biological equivalent of leaving your heater on when you leave home. But that's the shift that characterizes the evolutionary leap across the KT boundary from the Mesozoic to the Cenozoic. That it is the case, and this is very important, that the overall consumption increases. And it's a big deal, because I think most people have learned consumption is a bad word. I mean, it just sounds bad, doesn't it? The idea is that this is what you're supposed to, this is what makes human beings so terrible. We're consumers, we consume. But if you take a look at that, definitely across the KT, but also across the PT, you get an increase of consumption. And Vladimir Vernadsky, in fact, identified this as one of his laws of evolution, that one of the laws of evolution, the one thing that you knew was the case in the development of all evolutionary processes, was that you will always see the increase in the biogenic migration of atoms. That the rate of flow of that circulation will always increase. And there's a number of other elements that we won't discuss, but such as the fact that you will constantly see new elements included into that circulation in new ways over the course of development of the biosphere, in particular across these boundaries. But now what's interesting is now what's required this is where you get into the panic. You've been told, well, if you just keep increasing consumption, won't you run out? Isn't there an upper limit on that need for more flow? At some point, doesn't it become too late? So obviously, this is what we're told about ourselves. We're told that, well, for human beings, isn't it a problem that if you just keep figuring out how to use more and more energy, won't that be problematic? But this gets into the other concept I'd like to introduce. This is Lyndon LaRouche's concept of energy flux density. That is, in order to facilitate this increase in consumption, and again, you see this already in the biosphere, and we'll discuss why this is necessary for the biosphere, why the biosphere can never stop at a stable state, at a fixed system, and sit there, and we'll show it never has been able to. But then from that, why this is also necessary for human development. So this is what you see. Now, the ability to increase that consumption requires a focusing of the amount of that consumption that's brought to bear within a specific technology. So if you were to say I'll give you actually this one I think I don't have. Do I have it? No, I don't have it. Okay. To give you an idea, numerous things happen. The first is that if you look at the change in plant life across each of these boundaries, look at the change in plant life from the Paleozoic to the Mesozoic, from the Mesozoic to the Cenozoic. Actually, I do have this. Nope. You don't have it. I'll do that. I'll describe it. It shows up later in the amount of the density of what's consumed. I'll give you an idea of two things happen with plant life. One is its ability to photosynthesize, and the amount of photosynthesis that it performs increases. So you see a number of successive stages. You first see, in a period that extends even before where this chart begins, you see the populating of the oceans with photosynthetic bacteria. This gives you the oxygen crisis. You suddenly see a massive increase in the amount of photosynthesis which occurs on the planet because you see it begin. With motion onto land, you see a drastic increase in photosynthesis once again. You begin to see plant life on land begin to interface more and more with the sun. Now, again, they use the sunlight for something much more efficient than your environmentalist wants to use the sunlight for. They don't use the sunlight to create electricity. They use the sunlight to create things that fuel the entirety of that process of biogenic migration. They create the carbohydrates which form the basis for that food chain. And in fact, consistently over time, they figure out how to use more and more of that sunlight to create more and more expensive types of technology. Now, these start off in the Paleozoic. Your primary kind of plant life are ferns. Now, ferns are about as simple as you can get. Again, if we were to kind of give all plants a personality, the ferns would be your hippies. The ferns live near the water. They never leave it. They manage to live off the land. And the way they reproduce is they simply drop the sperm and the eggs into the water, hope they mate within the water. When they mate in the water, you get new ferns that now grow up on the edge of the banks of that same water. So it's a very tightly contained. It's again, it gives me the mental image of a hippie commune, the way you live, you reproduce, etc. With the development of gymnosperms, you get something that's decadent from the standpoint of that hippie commune. You get the development of a thing called seeds. And you have a whole process now of pollination and seed bearing, which now causes you to build an extra special case for your newborn plant that allows it to be carried further inland. but contains all the energy that plant needs to begin its development. So again, it's totally decadent. Suddenly you've got this pampering of the child by the plant with the gymnosperms. Becomes outrageous by the time you reach the Cenozoic, because at that point the seeds get wrapped in fruit. You can picture who's got the audacity to suddenly decide to waste all of that energy, massive amounts of solar energy, because the fruit the way we know, so that you can know that a fruit is much more dense form of energy than the seeds were themselves, is which would you rather eat? Would you rather eat the apple from the apple tree, or would you rather go munch ferns or pine cones? It's, there's much more nutrition energy value contained in fruit, packed into fruit, than there is in the earlier gymnosperms and ferns. Perfect, okay. This gives you an idea of the increase in the rate of just the increase in consumption of energy that's used per unit organism across the entirety of this process. Now, what I'd like to take a look at, so just so that gives you an idea, so that's very clear from the standpoint of Lyndon LaRouche's economics, the concepts of energy consumption, energy flux density. It's totally possible to find a single thread which runs through that entire process there. What I'd like to focus on here, though, is the point which is called a collapse point in this diagram. Now, that's the point where in animal systems, the prior system, which existed at a lower energy flux density, can no longer be sustained, and the subsequent system of a higher energy flux density has to take over. Now, in every one of these cases, as I said before, the subsequent system can be found in a research and development phase within the prior system. But the question is, what defines the collapse point? Now, you say, well, what is it that makes it so that one system must take over where the other one began? If we take a look at the systems, take a look now at the image here. If you take a look at the difference between the Paleozoic, the Mesozoic, and the Cenozoic, the timescales those are on, they're on a constantly decreasing timescale. So you've got a constantly increasing rate of growth, which defines the transition from one to the next. So take a look, the Paleozoic, that's 540 million years ago. The Mesozoic begins 250 million years. So between these, you've got, and then the Cenozoic is 65 million years ago. So the difference here between the period of time of each of these is almost an order of magnitude in each case, the amount of decrease. So you've got this rhythm, that steady increase. Not only do you get changed, but there's a rate that has to increase. That rate defines here the pink curve you can see inside of there, which we can refer to as our baseline. So we'll define that curve, that baseline curve, as the energy flux density requirement below which no system can fall without facing a collapse and having to necessitate something else to replace it. The systems which fall below that baseline suffer a violent correction, and that correction takes the form of a collapse. Now, all animal evolution has this form, that in order for an animal system to survive, the creatures that compose it physically have to vanish in order for a new idea to emerge. Now, that's important. In order to change the concept from one system to the next, the actual things that make up that system have to vanish. Now, we should be grateful that we don't do that. The equivalent of that for us would be that you'd have to die every time you wanted to change your mind, which is the case for animals. In order to change your mind, to change the concept, you have to die and become something else. But if you take a look at what human beings have done over the course of our existence, we've consistently experienced, within the existence of our species, changes that for animals only happen with evolution. For instance, the idea that we would totally change the kinds of territory that we live in, that we would transition from living from not living in desert areas, only living in temperate areas, to being able to live in the desert, an animal only does that with an evolutionary shift. You no longer change where you could live. The idea that we're now talking about being able to populate the Arctic, that doesn't happen within an animal species, but it happens within the human species. And a look at this, the chart that Bruce had pulled up before, makes that clear again, with the change in fuel sources from wood to coal to petroleum to nuclear. What's useful to see here is take again, like he said, look at the time scales. Again, the time scales here mirror what you had with the evolutionary time scales of animal growth, but much more dense. It's a continuation of that process. In fact, this image is not drawn to scale, because if you had drawn it to scale, it wouldn't be visible. The time we spent using wood before coal is 140,000 years. The time spent using coal before petroleum is 2,200 years. So again, you've got 2 orders of magnitude increase in the speed between wood, coal. Petroleum, we only have 100 years before we had the potential to go nuclear. That is the thing I'd like you to take a look at, because we're actually late for that shift. That shift should have occurred in the middle of last century. The technology appeared, but then you had an artificial, we were artificially prevented from moving with that technology as a platform by the environmentalist lobby, the anti-nuclear movement. Now, I want to show you that changing that rate of increase, making that break in our natural rate of increase, has necessarily disastrous effects. So now we have the ability to, with human beings, can consciously determine based on investment. So now where that intersection point takes place, where that intersection point occurs, you can pull that horizon line towards you and increase the rate of growth of your subsequent system. Can you play the one that's called Animation 2? All right. Now, the net effect of this, as you pull these back and you begin to add cones to the process, you can see 2 things happen for human development. One is that our actual development begins to approximate a different hyperbolic curve than you had initially defined by the animal system. But then second, that we manage to pull ourselves up off that baseline, which means that the successive move from system to system does not require a collapse to make that transition. Instead, this is a willful transition. Can you play the one called... Now, the environmentalist argument for sustainable development is to do the exact opposite. They say, well, don't we want to push that as far away as possible and sustain this one system for as long as we possibly can? Now, doing that will cause a very bizarre phenomenon, which is a collapse point without having a successive system to move to. Now, what's the physical expression of that? The physical expression is in the lie that comes up with what exactly is sustainable development. The fraud about sustainable development is that, well, shouldn't we just use windmills and solar panels? Because isn't that great? I mean, wind and sun, those are renewable resources, aren't they? But they're not. The actual cost, there is a real cost of windmills, of solar panels, which is, what are they made from? They're not made from sunlight. They're not made from wind. What are they maintained by? They're not maintained by sunlight. They're not maintained by wind. There's a real cost. The question is, does what they produce outweigh the cost for their own production? That's this question of energy density again. The problem with these as platforms is the collapse in energy density. The application of this as a policy will lead to a collapse. The form of that collapse will be various. The form of that collapse will ripple throughout the whole system as a systemic collapse, not as a single element. So you'll see the financial collapse, yes, but of necessity, famine. Of necessity, war. Of necessity, the kinds of social unrest that we're looking at right now and the causes of it. That this is something that you suddenly subject the human species to the same fate that you saw animal species before, a mass extinction event. Now, we can discuss some of this further, but that's just the image I want to draw out. There's a lot more that we've been doing as the taking this up as a project in the basement work, but I think it's something you'll find is totally clear, totally understandable, and something that's that we could use as the core of an educational program. But anyway, that's the picture there.